In this video, we're going to start talking about salt solutions. And a salt results from an acid-base neutralization reaction. So we're going to look at that first real quick. So when an acid reacts with a base, we're going to produce water and then a salt. And I'm going to look at this using Arrhenius theory first, because sometimes it's the easier way to think about it. Again, we produce water and a salt. And we'll talk more about the salts here in a few minutes, but just kind of a real quick example. Sodium hydroxide and then hydrochloric acid. So both of these are strong. And then again, if we think about it using our Arrhenius theory, right, my sodium hydroxide is completely dissociated, right? My sodium ion is separate from my hydroxide ion. Hydrochloric acid is completely ionized. So we've taken that covalent bond and we've broke it and produced two ions. And then we can think about combining these, and that's going to produce water. I know it looks kind of weird because I have a hydrogen ion and a hydroxide ion. Again, remember when we form water, it is a covalent bond. So we're going back to a covalent bond there. It is a pure liquid. And then we can combine the sodium with the chlorine. This time I would have an ionic bond. And then that is going to be my salt. And then, of course, using our solubility rules, that's actually completely dissociated also. And we will look more at ionic and not ionic equations here shortly. But right now, I just kind of wanted to give an example. So the deal with our salt. Some salt solutions are neutral. In this case, it would be. But some salts are actually acidic and others are basic. So kind of a big misconception. You see the word neutralization here and you think that you end up with a neutral solution when you're done. Not necessarily. Most of the time, it's actually not going to be neutral. So while the acid and the base are neutralizing each other, our resulting solution is not always neutral. Again, we just have to really be careful for those words this chapter. So the pH of our salt solution, in fact, let's just say first, the salt solution, right, which is my product, right? All I have over here on the product side, just to make sure we're all on the same page here, is salt and water. So what I have over there is a salt solution, right? I have a salt in water. So my acid-base neutralization reaction is producing a salt solution, if you wanted to say it that way. So the salt solution, right, my products, that results from a neutralization reaction is not, we're going to do a capital NOT and we're going to underline it, always neutral. And when I say neutral, I'm talking a pH of 7. So just because we take an acid and we react it with a base, it doesn't mean that we're making something that is neutral. So the pH of our salt solution depends on whether or not my ions in my salt are acidic, basic, or neutral. So the pH of the salt solution depends on whether or not the ions, right, that make up the salt, in fact, let's just say the salt ions is probably the quicker way to say it, are acidic, basic or neutral. Right? And what I mean by that, if it's neutral, it's basically going to be inert. Right? It's not going to donate a proton. It's not going to accept a proton. It's not going to react with water to form hydronium ions or hydroxide ions. Remember, when we determine if something is acidic, basic, or neutral, we're looking at the relative hydronium ion concentration to hydroxide ion concentration. So if it's neutral, basically those ions are inert. And in this case, my salt solution is, right? I have sodium ions, group 1A cation, those are always going to be inert. And then chlorine, right? That was the conjugate base of a strong acid. And we said that the conjugate base of strong acids were inert. They were not reactive, right? They're not basic. They're not going to accept a proton and go back, right? HCl is completely ionized. Cl- then is going to be an inert ion. So in this case, my salt solution actually would be neutral. If my salt solution is basic, what it means is one of the ions in my salt can donate a proton. Sorry, can accept a proton. Wow, got that backwards. So one of the ions in the salt can accept a proton from water. Producing a hydroxide ion, and then of course my conjugate acid. We'll look at an actual reaction here coming up. And then if my salt solution is acidic, right, one of the ions in the salt can donate a proton to water, right, producing a hydronium ion plus the conjugate base. So we really just need to look at our salt. Are salt ions acidic? Are they basic? Are they inert? If they're inert, it's going to be a neutral solution. If they're acidic, it's going to be an acidic solution, right? Because I'm going to produce a hydronium ion. Basic, I'm going to produce a hydroxide ion. So as a general rule, in fact, let's add a little bit more. As a general rule, salts formed by reacting and then our first one, and I'm going to abbreviate on you here, SA for strong acid, and then SB for a strong base. So if I take a strong acid and react it with a strong base, we're generally going to produce a neutral solution. Right? Remember we said that strong bases, we really don't think of them as having conjugate acids. And then we said that the conjugate base of a strong acid, right, is not actually basic. It's not going to go backwards. So if we take a strong acid, react with a strong base, we're generally going to get a solution that's neutral. Our second one, if I was to take a strong acid and react it with a weak base, so WB, we're generally going to produce an acidic solution. And again, we will look at examples. Number 3, switching those two, if I take a weak acid and react it with a strong base, we're generally going to get a basic solution. And then number 4, our only other combination we haven't looked at, a weak acid plus a weak base. In this one, it really depends on the relative strength of that acid or base. So it could be, these are horrible arrows by the way, sorry. Could be acidic, basic, or neutral. It just really depends which of those two is stronger. So if my weak acid is actually stronger than my weak base, it's going to be acidic. So if the Ka of my acid is larger than the Kb of my base, it's going to be acidic. Vice versa, if the Kb for the base is larger than the Ka for the acid, it's going to be basic. And if the two are the same, it's going to be a neutral solution because they're equally strong. The way I kind of think about it, just as kind of the shortcut way to remember my general rule, and again, we're going to look at reasons and examples, but just kind of a quick way to remember it, is that the strong one is going to win. So if they're both strong, right, neither one wins, and it's neutral. If I have a strong acid and a weak base, the strong one is going to win, which is the acid in this case, so I have an acidic solution. Right? Weak acid, strong base, strong one wins, the base is the strong one, so basic. And then when I get to the two that are weak, if they're equally weak, no one wins and it's neutral. If the weak acid is stronger than the weak base, acidic. If the weak base is stronger than the weak acid, basic. So really what we need to do is you need to compare. So it depends on the relative Ka and Kb values, right? We would need to compare them to each other, remembering the larger your equilibrium constant, the stronger the acid or the base. So Ka bigger than Kb, acidic, Kb bigger than Ka, basic. They're the same, neutral. I want to look in a little more detail on each one of these. So our strong acid, strong base neutralization reaction first. So we said these are going to be our neutral solutions. So looking at another example, let's use HBr as my strong acid. We'll use cesium hydroxide as my strong base. And then again, remember in aqueous solution, because these are strong, right? My acid is completely ionized. My base is completely dissociated. So if I was to make a beaker drawing of these, I essentially just have these guys floating around. My products, I'm going to have water. And you can think of this, if you think back to 150, 151, as just kind of like a double replacement reaction. Just be careful because water is covalently bonded, right? A lot of times we would say in 130 or lower level classes that you can just write it as HOH. And while you still can for balancing, if that helps, really remember that this is a covalent bond, right? It's not H plus and OH minus. It is when it's ionized, but when it's together, it's actually a covalent bond between them, right? Oxygen, if we were to draw its shape, is bent like that. So covalently bonded. And then we're going to take these guys and combine them. And then that's going to make my salt. And then again, using our solubility rules, this is actually completely dissociated, right? If I was to draw a beaker drawing of this, I have a whole bunch of ions in water, right? I don't actually have any compounds, right? My strong acid, completely ionized. My strong base, completely dissociated. My salt is soluble in aqueous solution, so completely dissociated. So again, I just have a whole bunch of ions floating around in solution, right? What we did here is we essentially drew or wrote our ionic equation. I do want to write our net ionic equation. And again, if you remember back to your chemistry past, this is where we cross out spectator ions. Remember, spectator ions are things that are exactly the same on both sides of our equation, right? Remember, a chemical reaction is a chemical change. Definition of a chemical change, we're producing something that is chemically different, right? So if you have something that's exactly the same on both sides, it did not undergo a chemical change, so we're just going to cross it out. So if I look at my ions, I'm looking at the things that I have written here, not the original one, right? On both sides, I have a bromine. So I'm going to just cross those out. It obviously didn't change, right? If I have Br minus on one side and Br minus on the other, it's not undergoing a chemical change. And then I also have cesium ions on both sides. That's not undergoing a chemical change, so I'm just going to cross those out. So my net ionic equation for this, hydronium ions plus hydroxide ions going to water. And then we did say earlier in this chapter that protons in water don't really exist, right? That proton is actually going to bond to water to produce a hydronium ion. So the better way to write this is to write H plus as H3O plus, right? Because that's what a proton in water does, right? This is an aqueous solution. So that proton's actually going to bond to water to form hydroxide ions. I have a hydronium ion, a hydroxide ion. I said that completely backwards, sorry. This proton is going to bond to this water to form a hydronium ion. This is my hydroxide ion, sorry for that. And then that's going to produce water. And then to balance this, I actually need to have 2 water in front of this. And then if we look at this, right, what do I have? I have my ionization of water reaction, right? I have the inverse of Kw, right? All I have is water. I got rid of my spectator ions. They were inert. They weren't doing anything. And I just have a solution where my ratio, right, between hydronium ions and hydroxide ions is 1:1. My pH is going to be 7, right? I have a neutral solution. My net ionic equation, right, for a strong acid, strong base solution is just this. So a pH of 7, neutral solutions. Let's actually write that. So what we need to be able to do eventually is if I just give you the salt, I don't give you the entire reaction, I just give you the salt, and we need to be able to recognize, is it acidic, basic, or neutral? So if I just give you, for example, potassium nitrate, right? What I need to recognize is that potassium ions, right, using our solubility rules, this is dissociated. Potassium's a group 1A cation. Those are always going to be inert. You can also think about it as coming from a strong base, right? KOH is a strong base, so potassium, it's not going to be reactive. And then nitrate, right, that's the conjugate base of a strong acid. And we had said that the conjugate base of a strong acid is not basic, it's inert. So this would be a neutral salt. If I asked what the pH of this salt solution was, we would say my pH is equal to 7.00. So a neutral salt solution. So kind of the easier way to recognize that, right? If the cation comes from a strong base, so potassium in this case did, and this is, remember, you need to memorize those strong bases. If the cation comes from a strong base, it's going to be inert. If the anion, right, is the conjugate of a strong monoprotic acid, be careful here, then it is going to also be inert. So let's write that down. So cations from strong bases So remember lithium hydroxide, sodium hydroxide, rubidium, cesium. That's supposed to be positive charges. It looks like I'm making a little cross. And then from group 2A, we also had calcium, strontium, and barium. So if your salt contains one of these ions themselves are inert. And then anions from strong, protic acids. Remember, sulfuric acid is diprotic, right? H2SO4, and I'll talk about that one also, but we're going to talk about it separately. So we had HCl, HBr, HI, right? So the anions from those, right? We said they're not going to take a proton and go back in the other direction, right? It's completely dissociated. So these are going to be inert, non-reactive ions, right? And then we also had a couple others. We had nitrate. I had chlorate and then perchlorate ions, right? All of those are the conjugate base, right? They're the anion that results when a strong acid ionizes. And again, we've said quite a few times, right? They're not actually basic. They're not going to take a proton and from water. So these guys are going to always be spectator ions. Again, remember, spectator ions are ions that are not reacting, right? They're not undergoing a chemical change, right? These guys are going to be inert. So if you get a salt that's made up of any of those combinations, right, one of those cations with one of those anions, the pH of that salt solution is going to be 7. It's going to be a neutral solution, right? Neither of them are going to react with water, right? Let's actually add that. I know I'm beating this to death, but I want you to get it. Not going to NOT capital to react with water to produce hydronium ions or hydroxide ions, right? When we looked at our reaction up here, red slash through it, soon to be an X, right? We just cross those guys out. They're not part of my net ionic equation, which I do expect you to be able to write. My pH is going to be 7 because all I have is this. I did say I would talk about sulfuric acid. So kind of just, you want to be careful for this. So H2SO4, I had said that only the first proton, right, is the strong one, right? This is diprotic, so it can react with water to produce HSO4 minus plus hydronium ions. And this arrow I'm just going to draw in one direction. But HSO4 minus can also react with water to produce sulfate ions plus another, negative, plus another hydronium ion. And then this one is weak. This one can actually go back in the other direction. So sulfate can take a proton from hydronium ions going back to form water and bisulfate or hydrogen sulfate. So you kind of be careful for this. I'm going to go and add and I'm going to put it in a slightly different color here, I can add HSO4- to this, right? That is the anion. Right here, anions from strong acids, and just the word monoprotic doesn't work when I stick that in the list now. But it is the anion from this strong acid. It's not necessarily inert though, which is why I don't like to put it here, because it can actually react with water to produce a hydronium ion. It's just not going to go back in the other direction. So when I'm looking at, is it going to be like acidic, basic, or neutral, I don't really like to include that one because, again, it can react with water to produce more of this one. So I tend to leave it off the list for that reason. Just remember, it's only that first proton that's strong. That second proton can react with water. Looking at a strong acid, weak base solution next. We should say a strong acid, weak base reaction, right? I just want to be consistent in my labeling here. So we did strong acid, strong base. Now we're looking at strong acid, weak base. So these are going to result in acidic solutions, right? If I ask the pH, my pH is going to be less than 7.00. Right? Remember, an acidic solution has a higher concentration of hydronium ions than hydroxide ions. As hydronium ion concentration increases, pH decreases. So my pH would be less than the negative log of 1.0 times 10 to the negative 7th. So less than 7. So with these ones, my anion comes from a strong acid, right? I have a strong acid. So if we go back up here, it's essentially this line, right? Anions from my strong acids, those are going to be inert. They're going to be spectator ions. However, the cation, right, from my weak base is actually a weak acid and will react with water to produce hydronium ions. So the anion from the strong acid is inert. It's going to be a spectator ion. We're going to cross it out, right? It comes from a strong acid. But the cation from the weak base is acidic, right? Remember, the conjugate acid from a weak base reaction is acidic. It can react with water. It will react with water. To produce hydronium ions. So increasing the hydronium ion concentration in my solution, making it acidic. So an example for this one, I'm going to use HBr again, and then I'm going to react it with ammonia, which is our weak base here. And then sometimes the water really isn't super obvious. It's an aqueous solution, so I'm always going to have water. When I balance this one, I'm not going to actually have water there. We just need to remember that I do have water because it's aqueous. Separating these, H plus, Br minus, right? Completely ionized. And then just looking at this base a little bit more, right? My base in water, right? It's a weak base. It is going to accept a proton to form ammonium ions and then hydroxide ions, but then it can go back in the opposite direction. So I am producing ammonium ions, and then I'm going to write it a little bit differently to start. And then I also have bromine. So my salt is actually ammonium bromide. In aqueous solution, right, this is completely dissociated using our solubility rules. But the actual salt, if you were to write it in salt form, right, not having it written in its ionic form, I do have those hydroxide ions. So if we kind of look at that, this is inert. But then if I go back down and look at this reaction, right, and this isn't my net ionic equation from this, this is just looking at my base, right, a closer look. That base, right, reacts with water to produce ammonium ions, but then, this is the one, this arrow, right, it goes back in the other direction, this conjugate acid, it is acidic, right? It can donate that proton back to water. So I have Br minus, which is inert, but I have this, which is acidic. So then again, going back up to this, right? My anion is inert, so Br minus. My cation, which is ammonium in this case, is acidic. It can react with water to produce hydroxide ions. And we will draw that here in a second. And let's just get some of this out of the way. If you haven't written it, just hit pause real quick. So if we were to kind of look at a net ionic equation for this, what I really have is Br minus. And if you were to put it in water, we would have to include that with the NH3, right, going to NH4Br. My Br minus, right, this is my spectator ion, right, it's going to get canceled out. It's inert. It is not changed. So when I write my net ionic equation for this, I'm going to have hydrogen ions, and I'm going to rewrite this again because, again, remember hydrogen ions in aqueous solution attach themselves to water. And I'm forming ammonium ions. And then that can go in both directions. So kind of if we wanted to rewrite it, H3O plus NH3 going to ammonium ions plus water. That would really be the better way to write it. And then we can see that water that we weren't seeing up above also. Right? We say it produces a salt in water, and then when we write it this way, sometimes it's confusing because we're just seeing the salt. But there is water because this is going to actually, right, bond to water to produce a hydronium ion, and then it's going to lose a proton to him, leaving a water molecule when I'm done. Hopefully that wasn't too terribly confusing. So I just want to look a little bit more at that salt solution. I'm going to kind of get a little repetitious here, but right, our salt, in this case, Na4Br, NH4 plus, Br minus, this inert, it's a spectator ion, it's the conjugate of a strong acid, it has no affinity for protons, however you want to say it, we don't care about it because it's not going to do anything. This reacts with water. So I want to write that reaction because this is how we're showing that it's acidic. So I'm going to take this salt, right, and that's, if we go back up, I have that here. It can react with water to produce hydronium ions. So that's what we're about to show, right? The cation from a weak base is acidic. It can react with water. So that's what we're about to do here. So reacts with water. NH4 plus. Right, I'm essentially writing my acid dissociation equilibrium equation here. We could write an equilibrium constant expression, set it equal to Kb, all of those kind of things. And then an acidic solution. Our next one is going to be a weak acid strong base solution. Or a weak acid strong base reaction, producing a basic solution. So this time my pH is going to be greater than 7.00. Actually, it's just kind of 7 infinitely, but we'll stick to our sig fig rules here. So this time, the cation for my strong base is inert, right? I have a strong base. If we go way back up here to these two statements, oops, I wanted to highlight. So the cations for my strong base, these guys are spectator ions, they're inert, they're not going to react with water. So because I have a strong base, its cation is inert. So the cation from the strong base is inert. And then this time, my anion and it's coming from the weak acid, is actually basic, right? It will react with water to produce hydroxide ions. An example, we'll use hydrofluoric acid and sodium hydroxide. And then remember, sodium hydroxide is a strong base. It's completely ionized or dissociated in solution. If I wanted to look a little closer at HF, right, it reacts with water to produce hydronium ions plus F minus. If I was to do a beaker drawing of that, right, I have both of those in solution. So when I write my net ionic equation for this, I'm actually going to keep it together. It's not completely ionized. I am going to produce water, right? We can think of the proton from my acid going to the hydroxide to produce water. And then my salt in this case is going to be the sodium ion from my base reacting with the fluorine ion from my acid, right? If you wanted, if it helps to write the equation, by all means separate these. Just remember that it's also HF, which means when I write the ionic or the net ionic equation, I'm not going to write those as dissociated because they're not completely dissociated. When you're writing your net ionic equations, only the strong acid and strong base ones do you want to write as completely dissociated or completely ionized. You want to keep the weak ones together. It's just sometimes to kind of like visualize the products, it's easier to do it this way because then we can think of this combining with this to make my salt. So if you need that visual, by all means. So, and then again, solubility rules. I don't actually have sodium fluoride in solution. I have sodium ions and fluoride ions, which means sodium, right? My cation from my strong base is a spectator ion, right? We go back up here, the cation from my strong base is inert, right? It's a spectator ion. We don't care about it. We just cancel it right out. So my net equation I have HF reacting with hydroxide ions to produce water plus my salt. Sorry, plus fluorine. I got rid of sodium already. Right, if we go back up here, maybe we should label that, right? This is my salt. Sodium inert. This is actually basic. It will react with water, and we'll draw that here in a minute. Right? It will react with water. If we go and look at this one, right? Remember, the conjugate base of my weak acid solution is basic. I do have an arrow going in this direction, right? It will take a proton from hydronium ions to form HF. So it will react with water. I couldn't draw something like this for a strong one, right? I only have an arrow going in the forward direction if it's strong. But because this goes in the both directions, we know that it is reactive, right? The conjugate base of a weak acid is basic. The conjugate base of a strong acid is not basic. So back to this again. Will react with water. And we're going to draw that. So F minus. I'm writing a base dissociation equilibrium equation here. I'm going to produce hydroxide ions plus my conjugate acid. So a basic solution. My pH is going to be greater than 7. Right? Kind of going back up and comparing these. I know it's getting kind of messy, but when I looked at my, it's up a little bit here, my strong acid weak base, right? I ended up down here with an acidic solution, pH less than 7. And when I scroll all the way up to my strong one, right, we ended up with just water. So pH equal to 7, right? It's a neutral solution. That says neutral solution. Not that you could ever read that in a million years. So just one more for us, and that's going to be a weak acid, weak base solution. I keep saying solution, sorry about that. A weak acid, weak base reaction. And then whether it's acidic, neutral, or basic depends, right? We just have to look at the relative Ka and Kb. We have to compare those to each other. So it could be acidic, basic, or neutral. Right? We know that the cation from my weak base, right, is acidic. We know the anion from my weak acid is basic. So it just depends, is that acid stronger than that base? So the cation, right, from the weak base is acidic. Right? It will react with water to produce hydronium ions. the anion from the weak acid is basic, right? It will react with water to produce hydroxide ions. So kind of our example here, HF plus ammonia, right? We know we're producing ammonium fluoride, right? It is an aqueous solution, so I do have water. So then if we look at the actual salt here, I have NH4 plus and F minus, right? And we've already written both of those reactions. If we go back up, I know F minus reacts with water to produce hydroxide ions, giving us a potentially basic solution. I know that ammonium ions react with water to produce hydronium ions, giving me a potentially acidic solution. So which is it? It just depends which of these two is stronger. So will react with water to produce H3O plus, will react with water to produce hydroxide ions, right? Is acidic, is basic. So we need our Kas and Kbs for these, and I have them here for us. So my Ka for ammonium ions is 5.6 times 10 to the negative 10th. And then my Kb for fluoride is 2.9 times 10 to the negative 11th. So then comparing these two, right, my Ka times 10 to the negative 10th is a larger number than the negative 11th. So my Ka is larger than my Kb. So this solution is going to be acidic. You really just have to compare those two numbers. If they were same, right, it would be a neutral solution. If Kb was larger, it would be a basic solution. I do want to summarize our salt solutions here. So let's make a summary. So we'll make a little table. Let's have our neutralization reaction. And then we'll have our salt solution. And then we're going to have something about our cation in our salt, and then the anion of our salt. So our first one will be strong acid, strong base. Our salt solution is going to be neutral, right? pH equal to 7. I didn't leave myself enough room for 0.00. My cation is inert, right? It's going to be a spectator ion. It's going to be neutral. It's not reactive, whatever sort of wording you want. And then the same with our anion. So those guys are not going to be reactive. If we have a strong acid and a weak base, we're going to have an acidic solution. My pH is going to be less than 7. Barely squishing that in there. And then my cation is going to be acidic, right? It will react with water to produce hydronium ions. And then my anion is going to be inert. A weak acid and a strong base. These are going to be basic solutions. My pH is going to be greater than 7. This time my cation is neutral, right? It's my spectator ion, it's inert. And then my anion is going to be basic. And then our last version is if they're both weak, right? My salt solution, it really could be any of those things. So it could be acidic, basic, or neutral. My cation is going to be acidic, and my anion is going to be basic. And then again, remember to tell whether overall our salt solution is acidic, neutral, or basic. You want to compare the Ka of the acid to the Kb for the base, right? Whichever one is bigger, that's going to have the stronger corresponding molecule, right? So if my Ka is bigger, then it's the stronger acid. If the Kb is bigger, it's the stronger base. So let's look at some examples where I just give us the salt, and then we have to say, is the salt acidic, basic, or neutral? So I'm just going to list a few, and then I really want you to try to do these on your own. So hit pause, and then when you're ready to check, hit play again. So are the following salts acidic, basic, or neutral? And then I need more information to tell is also an option, right? You can't tell if the salt comes from a weak acid, weak base solution, right? We would need the Ka and the Kb to be able to tell. So that is also an option. So I'm just going to list them here. So this is together. We need 3 hydrogen here. And then an iodine. So this is enough to get us started. So again, please hit pause, do these yourself, and then when you're ready to check, hit play again. Alrighty, so the way that I would approach them is to just look at the 2 pieces, right? So I have sodium. Sodium is one of my inert cations. We don't care about that. ClO2 minus is not the conjugate base of a strong acid, right? It's the conjugate of a weak acid, so it is actually going to be basic, right? If we go back up to our table, if it comes from a weak acid, my anion is going to be basic. So this is going to be a basic solution, right? ClO2 minus does react with water. Didn't give myself enough room here, but we would produce hydroxide ions plus HClO2, right? Because hydroxide ions is one of the things I'm producing, I have a basic solution. So the 2 components of my salt, again, group 1A cation, it's inert, it's a spectator ion, we don't care about it, so that's not doing anything. And then when I look at ClO3 minus, it is the conjugate base of a strong acid, so because of that, it's actually not basic neither, right? This is from a strong acid, right? It's not going to accept a proton and go back in the other direction. So this is going to be a neutral solution. And I could ask this question in terms of pH. I could say, is the pH equal to 7, greater than 7, or less than 7? Which is a perfectly valid way to ask the question. So pH greater than 7, pH equal to 7. Next one, I have lithium and fluoride ions. Again, group 1A cation, I don't care about it. It's a spectator ion, it's inert. F- is from a weak acid. So it's going to react with water to produce hydroxide ions in my conjugate acid. It is going to be a basic solution, right? pH, again, greater than 7. And then the same thing for this one. I know that looks kind of weird. What I just remember is if I have nitrogen bonded to 4 things, and this is not its Vesper shape, this thing would be tetrahedral, but if I have nitrogen bonded to 4 things, it has a positive charge, right? Ammonium ions. If I have nitrogen bonded to 3 things, I have ammonia. I have a lone pair on here. So just kind of like looking at these 2 examples, ammonia on the bottom, right? This is my base, this is its conjugate acid. Or you could say this is an acid and this is its conjugate base, however you want to do that, but those are conjugate acid-base pairs. What we're doing with this problem is I'm just replacing one of those hydrogens with a CH3 group. So I still have nitrogen bonded, right? The one I just did on the bottom would be its conjugate base. So I still have nitrogen bonded to 4 things. It's just 3 of those are hydrogen and 1 of them is a CH3 group. So it's essentially, you can think about it as very, very similar to ammonium ions. Again, we just replaced one of the hydrogens with that carbon group. So it does have a positive charge. I have I-. I- is from a strong acid. Right? So it's inert, it's not reactive, but this, however, is a weak acid. So this is going to be an acidic solution. My pH is going to be less than 7. So just one last thing on this topic for now, and that's small, highly charged cations. Those are also acidic. So just kind of a special note, and we don't see these a lot, but I do want you to be able to recognize a couple of them. So small, highly charged cations are also acidic. So something like aluminum, magnesium, right? Both of those can react with water to produce hydroxide ions. So kind of along the lines of those examples we were doing above where I give you a salt, if I was to give you something like magnesium nitrate, I do have magnesium ions, and then I have 2 nitrate ions. Whether I have 1 or 2, it doesn't really matter. It's still the conjugate base of a strong acid, so it's inert. But this is acidic. So just watch out for those guys. If I was to give you, let's say, aluminum bromide I don't care about, but aluminum would be acidic, right? They do react with water. They form complex ions. So like if I was to take, I had just said aluminum bromide, so let's look at that one, Br3, right? If I take that, it does separate into aluminum with a 3+ charge, and then my 3 bromides, right? These guys are inert. but that aluminum actually can react with water, and I form a complex ion. So aluminum will react with water to actually bond to it. Water is neutral, aluminum has a 3+ charge, so this would be considered a complex ion. A complex ion is where you have a small molecule bonded to your metal ion, or your cation, we should say. And then I could have another water molecule. This is aqueous. And that forms, this is kind of messy looking. I'm going to have 5 waters. Let's move this over because I'm going to run out of room. Instead of 6, one of those 6 water molecules is actually going to give a proton to this water molecule to form hydronium ions. And then this still has a +2 charge, but I have an OH group also attached to it instead of the 6 waters. I'm not sure. I just want to make sure you guys are following that because it's kind of weird. So I had 6 water molecules that are essentially bonded to that aluminum, because water is neutral and my aluminum, right, has a +3 charge. If I'm going to bond things that don't have a charge to something and that has a +3 charge, the whole thing still has a net charge of +3. And then what's happening is one of those hydrogens from one of those waters is actually going to bond to this water molecule that's going to make hydronium ions. What that leaves then is I have one of those water molecules missing its hydrogen, right? Because it's hydrogen bonded to this to make this. So now that's in the form of an OH. I still have 5 waters. OH normally has a negative charge, right? It lost a proton, so I now have a +2. I'm not going to ask you to draw that. I'm only drawing it so you can see that I have an acidic solution. So if you have something like aluminum, magnesium, there's a few others, and it's in an aqueous solution, it is acidic because of this reaction. And again, I won't ask you to write this reaction, but if I give it to you, kind of be able to tell what's going on.